Okay, this is a bonus recording. You may find this interesting. You're not required right now to know all this material, but it kind of ties in how color works. I found that in a lot of classes we talk about things like the JPEG compression and we treat everything as if it's black and white. And the reality is that we have color. So a few things about a general image storage system. We see in red, green, and blue, essentially, and I'm going to explain more of that in a minute. But when we actually do our image compression, it's common to transform that into another color system. And there are reasons also that we'll explain why, but that's the YCBCR block that we have here. Then finally, it's common to downsample the color information, keeping only the brightness information. When we're all done, we upsample the color information, the chrominance, transform back to RGB, and then display it. Okay, so you've probably seen this before. We can take white light and we can separate it into different colors. We have long wavelengths, which are lower energy and lower frequency with the red. Beyond that, there's infrared, and then we get all the way down to what we generally consider as RF, but it's all part of the same spectrum. Moving up, we have orange, yellow, and then green. Beyond green, we have blue and violet, and then we get to where we can't see. Up in the ultraviolet and getting into higher energy, we have X-rays and gamma rays and so on and so forth. So our eyes are contain cones and rods. The cones can see color, and we have three types in general. There are a few people that have four. There are animals that have many more and animals that have fewer. So we have cones that respond to red. Now they don't respond to a single wavelength. They have a response illustrated here in red, where the relative sensitivity is dependent on the wavelength. And then we have cones sensitive to green. And as you can see, their sensitivities overlap substantially. And then we have our cones sensitive to blue. So if we then separate anything that we see into its red, green, and blue components, we can ideally excite the red, green, and blue cones to create any color we want on the palette. But there is a problem with that, and we'll talk about that. But that's the basic idea. Since we can only receive distinctly red, green, and blue, then this infinite dimension of light, color, or spectrum can be projected onto three basis functions. And this would actually work really well, except for a problem that we'll come across in a minute. So since we're dealing with light, if we add different light colors together, if we add them all together, we're going to get white. So we would be looking right there in the middle. And if we add the green and the red, we get yellow. And in fact, you can see in here the middle, we have the cyan, magenta, and yellow that's used in printing. So although we're not going to spend a lot of time with CMYK, CMYK is a subtractive thing instead of additive. When we're putting light together, we're adding it. When we're putting on pigments, we're putting in things that absorb certain wavelengths and subtract. So if we have white light coming in and we put yellow paint or pigment, it will absorb the blue, and so only the combination of the red and the green will reflect, giving us a perceived yellow color. So we actually have we have 3 dimensions here, red, green, and blue, so we get a cube. When they're all present fully, we would have white, and when they're all lacking completely, we would have the black that's right there. I won't spend a lot of time with this, only to say that in general we have both cones and rods. Cones see color and the rods don't. And they're interspersed in kind of a random pattern. But the important part about this random pattern is that there are more green than the other two. Well, if you look at this from an evolutionary point of view, people living in a world with plants, being able to distinguish subtle shades of green is very important. More important, perhaps, than discerning whether or not the sky is above us or below us. And we have very few blue receptors. Quite a few red also. So between the red and the green, we can discern a lot of what's going on in the natural world around us. Okay. Well, there is no single red color. There's no single blue color, no single green color. So when we're deciding which colors to use, which specific wavelengths are red, green, and blue, it has an impact on what colors can be represented. So if we look at the entire color space, which is only represented here, I guess, symbolically, because you're looking at this on a red, green, blue monitor. But your choice of which red, green, and blue wavelengths you use determine the kind of range of colors that can be represented. So sRGB has a smaller range of colors than Adobe RGB. As you can see, this triangle is a little bit smaller. Okay, we'll see why we have these problems and we can't see every color with just red, green, and blue, as seems logical. And actually, first, I guess I should lay a little bit more groundwork so you can see where this is going. So if we have a basis function, and here we have the basis functions are our 3 colors, we could transform that to another basis. And it makes sense to try some that are in the family of the HSV ones. Here, hue gives us the color, the red, the redness or blueness or greenness or whatever else is in between. Saturation tells us how vibrant that color is, or how pure, how far it is from gray. And value tells us how bright it is. So this is a really nice, easy coordinate system to work in. It's pretty intuitive. So it gives us kind of tint, shade, and tone. So when we talk about colors, there are different ways kind of consistent with this that we can talk about it. One is luminance, the brightness. That matters a lot. And this makes a lot of sense because if we were in, say, a situation where it's low light, you might notice that you can't see color very well. And that's because the cones require more brighter light to be able to distinguish colors. The rods require less light, but they don't distinguish colors. So our eyes in low light really don't see in color. Or if they do, it's not very much color. So luminance is a natural thing for us. It's just the brightness. Chrominance would be the amount of color, and that's, as we've talked about, the hue or saturation. Okay, so as with any finite basis transformation, it's done by with a transformation matrix. and here's the transformation for one of the color spaces. This one is, in a way, it's similar to hue saturation value that we just described, but this is slightly different in that we have the luminance, which corresponds to the value, and then instead of hue and saturation, we have two chrominance, and the two of these contain the dimensions of color, and they're called the CBCR in some spaces, or some applications, and UV in others. There's some CBCR is used in, say, video or television broadcasts. We won't go into some of the subtle reasons there, but let's take a look at what really we have. Here you can see the Y, which is the luminance. Actually looks like a beautiful black and white version of our original image. The other two don't make as much sense, the U and the V. But one thing you can probably tell by looking at them is that the Y looks the luminance looks very detailed, and the others don't look very detailed. Well, part of that is the reason is because our eyes are just not sensitive to those dimensions as much, and we take advantage of this when we do compression, and I'll talk about that in the next slide, by downsampling. But there's something else I want to bring up and point out while I have this thing before me, and we'll bring this up again later, but that is this matrix transformation, this transformation matrix has some negative values in there. So if we transform light, RGB, which is going, 0 means none, and 255 means on all the way, fully bright. Using a matrix like this, it's possible that we will get negative values. And so we have to add this offset to make them positive. But these negative values are going to come back to haunt us in several ways. Whoops. So, first off, the downsampling. As I'd mentioned, we're not as sensitive visually to the chroma dimensions as we are to the luminance dimensions. And so we always keep all of the luminance dimensions, but the chroma dimensions we may downsample either, and we do this in different dimensions. So here, for example, in the left column, labeled 444, we have our image. The luminance is the top, and the two chroma are the bottom two, CB and CR. Well, we may also, for the 422, take the, we always keep the full luminance, but we get rid of half the samples of each of the chrominance channels. And in the final one, we actually get rid of 3/4 of the chrominance samples. And so, this is represented kind of like this, where we have our luminance shown as this block. Each one of these represents a single pixel, and the chrominance are behind it, that block, showing the two dimensions of the chrominance. And so it's just a way of representing the brightness and color information associated with each pixel. When we downsample the chrominance, we keep the luminance for every pixel, but for every other one, we drop the chrominance. And when we go to the 420 one, we get rid of the chrominance for all the color information for 3 out of every 4 samples. But actually what we do is we average the color information for those 4 pixels, and it's shown right there. So this is actually what's used primarily in video coding. We really care about the detail of the brightness or the value, the luminance, but we don't care about the color nearly as much. There are different ways of doing this. Here's MPEG-2, and we're actually going to skip our discussion of CMYK right now. But here's the problem. When we are in one color basis and we transform to another, remember, we cannot use negative colors. We don't have negative light. We can't shine a little bit of negative red to make the greens pop, for example. And we can't apply an ink that produces light. All we can do is apply inks that absorb light. So we're only dealing with positive values. And when we only deal with positive values, there's a limited range to what we can actually represent. It's more limited than what we can actually see. And then additional problems come in that we don't have, although we're getting really good with illuminators. We have these LEDs that work great. We don't have perfect inks. And so what can be produced on a printer is actually even more limited than what can be put on a display. There are some exceptions to this. This is it for your standard CMYK printer. If you do professional printing, they may have more colors, and maybe 10 or even 20 different color inks that they use so they can produce a wider color space. I know a professional landscape photographer who has his own setup. He found that he couldn't get the color accuracy he wanted with any of the places, so he got his own printer. It costs $250,000. It prints colors that can't be displayed on your normal screen. And so I'm not sure how he does the editing to get those colors to look out right on his printer when he can't even display them accurately on the screen. Maybe you need some mind-altering drugs. I don't know. But the only way to get more colors on a printer is to have more inks. Okay, so let's talk about just a few other things, and then we're ready, I think, to get into the image compression. And that is when we convert something to black and white, our eye is about 70% relatively sensitive to green, 20% to red, and 10% to blue. And this varies per person, so it might be 60-30 for red and green. So here's a picture of a dogwood flower. It's a pink one. And when we convert this to black and white, we can do it in many different ways. One of the ways on the upper left is just to average all the colors together. And sure enough, it's a black and white image. On the lower right, we weight the green more heavily. So what happens is parts of the red flower don't show up as brightly, and so now they're dark because the red isn't contributing as much. Blue is pretty much right out of this image to begin with. And then in the background where we had let's look there, green, it shows up more brightly. So sometimes a photographer trying to isolate a particular thing will do his color transformations with varying amounts of the different colors. Okay, so now let's look to see what we have when we use the YUV transformation. On the left, another nice black and white image, and it helps maybe to go back and forth. Look, for example, at the center of the flower. It's very different in these 4 representations. So the left is the YUV. The right is another one called Lab. it's clever. L is for lightness, and then we have the A and B channels for color. And so we look at the lightness from the lab view, and it's kind of a pleasing effect. But certainly you get a big change in what's going on in the center of the image. Many different color spaces that we can work with. Okay, so pardon me for just a moment while I check my notes. Yeah. Why do we have so many color spaces to choose from? Well, it comes down to, once again, the fact that we cannot fully represent any color. Because if we go back and represent, say, we shine with a green LED at a particular wavelength, we're going to also be exciting the red. So if we wanted to get a red that was, say, out here on the spectrum, we would essentially need a red LED that did not excite any of the green. Okay, so that's probably possible. We can choose that as a wavelength for our red, something clear out here. But if we wanted something over in this range, we're going to need to control how much of the red and how much of the green are actually present. And since we don't have an independent control of the green, anytime we shine green, the red is going to respond somewhat. We have a difficulty that we can't arbitrarily represent any color of green that we may choose. And the same goes for, well, blue is actually pretty good. We can come over here and choose something that excites blue. But one thing to note is this doesn't go all the way down. It's hard to tell exactly what happens as we go further down in here and to get the data. But since these are non-orthogonal and actually severely overlapping basis functions, it's hard to build up exactly what we're looking for as we do this. So going back. All right. Actually, let's stop there for color, and then I'll talk about how this works with JPEG in the next lecture. So thank you very much.